to begin with, we're going to have Daniel Brown. And I'm going to give you his Twitter handle so you can spam him afterwards with all the questions that you didn't ask here. So he's from the University of Oslo. And he's going to be talking about resting state fMRI connectivity in, thank you, connectivity in schizophrenia, bipolar disorder, and healthy controls. He is a master student in Lars Westlight's web, and he was a student in a Neuromatch Academy. And for everybody here who didn't do that yet, next summer, be a student at NMA. It's going to change your life. Okay, Danny, take it away.
Thank you, Marius. Thank you, everybody, for being here today. As Marius mentioned, I'm a master's student. I just started learning computational neuro, so would love to get everybody's feedback and just here to learn as much as I can. So the title of my talk is Resting State fMRI Connectivity in Schizophrenia, Bipolar Disorder, and Healthy Controls. And I'm a master's student of cognitive neuroscience here at University of Oslo. I'm working with Xiqin LIU at Normet, which is the Norwegian Center for Mental Disorders Research. And I'll just dive right in. So we're looking at connectivity analyses, which I'm currently learning. And so the gold standard, or what we're really looking for in this, is biomarkers for mental disorder. And why that might be something we really want to find is because this could improve the reliability of diagnoses of mental disorder. For example, if we could just use a method like EEG or fMRI and kind of peer into the brain and see how everything is working, then we could understand maybe this person, we could make differential diagnoses. And increasingly, we're starting to realize that within mental disorders, they're not all the same, meaning that there are distinct subtypes of many mental disorders, like, for example, depression and maybe schizophrenia as well. So this opens up a translational impact where if we knew what type of subtype of, say, depression or schizophrenia one person has, you could map that to the ideal treatment for, that we've determined through basic research. And increasingly, I'm beginning to, and I know that a lot of other people are starting to think of these mental disorders as circuitopathies, meaning that distinct circuits can be implicated and lead to these different subtypes of mental disorder. So how do we do these connectivity analyses? Well, in the research, we use these graph theoretical constructs where we have nodes that are usually parcellations of the brain, and then we have the connections between those nodes, which are the edges. And there's different types of measures of this connectivity. We can have effective connectivity where it's directed, meaning we have a parent node and a child node, and that edge is a connected, directed, a directed connection between those nodes. Or we can also just have functional connectivity with undirected nodes, basically just correlation between nodes. And there's been all types of computational methods to look at this, like Granger causality, dynamic causal modeling, and each one of them. Yes?
We can only see your first slide. Sorry to interrupt.
Oh, I'm so sorry.
Maybe you're sharing the wrong screen. I don't know what's going on.
I'm not sure either. Oh, it says sharing is paused. Okay. I had some type of issue here. Just 1 second.
Don't worry.
Are you able to see my screen?
That is better.
All right. So, so I've been talking with just the first slide, huh? As I said, the gold standard here is we're looking for biomarkers for mental disorder, thinking along the lines of circuitopathies and graph theory. So we've got all these different connectivity analyses like Granger causality, DCM, and they have common pitfalls and they also have common or different benefits, each of them do. So we wanted to figure out which one should we try to use. And the one that we wanted to use is a relatively new one called the DGM method, which is a dynamic graphical model. So the big paper here is by Schwab and colleagues from 2018. and they described this model and also try it on some ground truth data. They made some synthetic neural data and then tested this model out compared to other connectivity analyses. And this is a model for directed relationships, so directed connectivity. Without getting too into the weeds here in the interest of time, one of the things that DGM does, which is shown at the bottom, is it compares different models of connectivity. So it compares bidirectional connection for each pairwise node combination. So from A to B, from A to C, from all the different nodes. And it tests it for being a unidirectional from A to B, or a unidirectional from B to A. And it also tests a bidirectional. And then it tries those out and using a log Bayes factor, picks which one kind of wins in this battle and then assigns that to the model in an extremely simplified method of explaining. So what we wanted to do is use our data that we have at Norment. This is the top data set, thematically organized psychosis research. This was collected beginning in 2002 in 4 major hospitals in Oslo. To the bottom left, you can sort of see the breakdown of these with how many individuals with bipolar disorder diagnosis, schizophrenia, healthy controls, and other. We also used some data from a stroke sample that was collected using the same paradigm to get some additional healthy controls in there. You can see to the right-hand side on the bottom, we have our image acquisition specifics, where it's a 3 Tesla scanner, 3 millimeter voxel size, and we're looking at resting state fMRI data. The TR is 2.25 seconds, and there's 200 total scans for each individual. So individuals are sitting in the scanner, just kind of mind wandering, and that's the data set with 200 time points, 2.25 seconds apart. So our very preliminary findings, just to show some data, to the top right, you see our top sample in the DGM method. So the way to read this is on the left-hand side, we have our parent nodes, and on the bottom, we have our child nodes. So that's the directional, the direction comes from the parent to the child. And the first thing you'll see is that we have really strong connections bilaterally. So from the right BMPFC to the left, and from the left to the right. So that's what these diagonals are. But before I go in and look at anything else from this, this model, I want to point out what I have on the bottom right here, which is our average discount factor. So this is a parameter within the model that measures the variability of the nodes and their variability across time. And when this number is really close to 1, it means that there isn't any variability if it was a purely 1. If it was 0, it'd be completely uncorrelated and just noise. And through some conversations with our colleagues, we've heard, and they've run this on other data sets, this parameter is usually in their data set was about 0.8, 0.7. And so we're seeing from this that there isn't a lot of variability in our data set, and we're kind of trying to understand why is that. So the limitations that we're bumping into now is that we have a really, we have a small number of time points in the sample. So, and it might not be enough to do this kind of method. There's only 200 time points in the sample, and then the TR is also very long. So that's a time in between the scans. So if we're talking about these, the dynamics in this system, in a neural system, and we're taking measurements 2.25 seconds apart, are we really going to be able to tell anything interesting, or does the brain act faster than that? And other things that are important, like I said, the variance in the nodes, maybe we just don't have enough variance in the data, maybe we need more data. And there's also, motion can also be interesting. So, and I should say, we reran this. We originally had our data thresholded for noise at a certain threshold, and we turned that threshold down, thinking that maybe we'd introduce some more variation into these nodes, and that did not, change our discount factor, move it further away from 1. So with that, I want to leave as much time as possible for us to talk about this? Does anybody have any ideas where we should go with this next? Our first ideas are to try either a new method with the same data set, or probably more likely a different data set that has a shorter TR and maybe more actual scans, more time points. Great, thank you guys.
Oh, that was awesome. Okay, I don't see any questions yet in the Q&A or in the chat. Let me scroll in the chat, see if I missed something there. So people start typing your questions. Oh, Marco, do you want to ask a question? Go ahead.
Thanks, Daniel. Very nice presentation. I'm sure you said this. I probably missed the part with, but so you said that you're looking for biomarkers, so of these conditions, and I'm not sure I understood how this directionality can act as a biomarker.
Mm-hmm. Yeah, sure. So, for example, the only thing that we're showing in, or that I'm showing in this graph, and that, you know, that's because of the shortened time period, is this is everybody put together. This is the entire top sample. But if you were to look at this same model of across group differences, right, where you have healthy controls graphed in one, schizophrenia on another one, and bipolar disorder on the other, you might see this different pattern where maybe this connection is really strong in schizophrenia, or is like flipped in bipolar disorder or something like that. So what we do is we take these models and then we do group differences, and we look at the differences between them. We compare them.
So this is currently based, this N1000 is what sample? Sorry.
Yeah, this is on the bottom.
The total sample. Okay.
Yeah, and it's just from top in this scenario. But that includes.
So it combines both healthy controls and patients. I see.
Mm-hmm. Yeah, and because of this discount factor, we kind of like haven't even been able to progress to what we really want to do, which is the group analysis, where we start to answer that question that you were asking.
Okay, Dipanjan, do you have a quick question?
Yeah, so I have a couple of questions. So I think I can read the paper about this particular method you were describing, but from this from this present slide, so you mentioned the present slide that you presented, the result. Can you go to the result, please? Yeah. So as it is, I understand it's a effective connectivity. Is it effective connectivity? Like, so then why this connectivity appears to be symmetrical, like this matrix? Like, I mean, the connectivity which is, so can you please explain on those things? I mean, of course, I don't know much about details about this particular method.
It's a very good question and something I hadn't considered, but the first thing that I can think of is that it is directed, but it doesn't seem that it's limiting to only one direction, if that makes sense. Because like I said earlier, it's comparing these three different models. So it could be a bidirectional connection. It's also compared to unidirectional from B to A and one from A to B. So yes, it could be the case that A to B, a unidirectional wins, but also a bidirectional could exist. So I think that's the answer. And that is my work right now. Yeah.
So here in your data set, you mostly find bidirectional connections, you mean, like which is similar.
Yes, if we were to like interpret this, I mean, well, you know, the strongest ones are these bidirectional ones, and that's exactly what you will see in this model all the time, because they're the two hemispheres of the brain. You know, they're corresponding regions. But then there are also all these other connections that show up, but really we're not even interpreting this because of this.
Mm-hmm. Yeah.
Very fascinating. But we have to move on, unfortunately.